Hello and welcome to my presentation on stellar mass black holes. This presentation is by Anirudh Nanda. So black holes are a particular interest of mine, especially since they're a very unique concept to me. So black holes are generally misunderstood, and as such I wanted to understand more about black holes. They're seen as a generally, scary type of astronomical object, and that's basically why I'm interested in them. I'm especially interested in black holes that are the same size as solar masses, and these are also called stellar mass black holes. So the existence of these fascinates me, especially since it's a very foreign topic. As explained by the University of Chicago, black holes are essentially large interstellar objects that are the result of large stellar masses collapsing upon itself, forming a singularity point, where large amounts of mass are compressed into a very tiny volume. This essentially creates a gravitational force so incredibly strong that even radiation and light can't escape it. This in turn creates a sort of viewable black hole, which is called the event horizon. The event horizon is basically the region where light cannot escape, and neither can radiation, and as such, the absence of light makes these black holes quote-unquote viewable. Stellar mass black holes have sizes comparable to extremely large solar masses, and can range up to 100 times our own sun's mass. Supermassive black holes are those that are found at the center of large galaxies, and are more than 100,000 times the mass of our own sun. The Milky Way supermassive black hole is called Sagittarius A star. This supermassive black hole is nearly 4 million times more massive than the sun, which is equal to 4 million solar masses. Intermediate black holes, as the name suggests, are the black holes occupying the category of mass between stellar mass and supermassive black holes. No matter how small or how big, black holes are still capable of growing. However, this presentation will focus primarily on stellar mass black holes. As mentioned before, stellar mass black holes are a special type of black hole, with similar masses to the largest suns. Notice how I bolded largest here. This is because only the largest of stars are the most likely to become black holes. Simply put, smaller stars, after they collapse, will more likely become white dwarfs than stellar mass black holes. Our own sun, when it implodes, will most likely become a white dwarf, and not a stellar mass black hole. Stellar mass black holes can be formed by various methods, and these include the merger of two neutron stars or the collapse of a single star. However, most stellar mass black holes are formed by singular solar mass collapses of stars many times the mass of our own sun. In other words, only larger suns have the potential to become stellar mass black holes, and these are proved by the TOV and Chandrasekhar limits, which I will discuss later on. Any black hole forms from a collapsar, or a stellar mass which has imploded upon itself due to gravitational collapse from lack of fuel. Collapsars that exceed the TOV, also called the Tolman-Oppenheimer-Volkoff mass limit, become stellar mass black holes. Collapsars falling below this limit typically become neutron stars or white dwarfs, which is set by the Chandrasekhar limit. The TOV limit of neutron stars ranges from 1.5 to 3.0 solar masses. Collapsars greater than or equal to this limit can become black holes. Interestingly, 1.5 to 3.0 solar masses is approximately equal to the remnant mass of main sequence stars, with nearly 15 to 20 solar masses. Main sequence stars refers to stars that are in the main sequence of their life cycle, normal stars. And remnant mass refers to the remnant mass after the star is imploded. As such, we see here that according to the TOV limits, only stars with masses greater than or equal to 15 to 20 solar masses have the capability of becoming black holes. Stellar mass black holes in isolation are difficult to find or identify due to their extreme gravitational pull after their event horizon. This is because there is not enough light or radiation to effectively discern the event horizon from the rest of space. However, these black holes are much easier to find in certain types of solar systems, known as X-binary solar systems. In X-binary solar systems, there are two solar masses. One solar mass is a normal star, while the other is a collapsar. Collapsars, like mentioned before, can include a neutron star, white dwarf, or a stellar mass black hole. Some X-binary systems can include a normal solar mass and one stellar mass black hole. In these systems, the stellar mass black hole has such a large magnetic pull that the gases from the normal main sequence star are pulled into the black hole, which makes it much more visible. In addition, this gas, which is heated to many thousands of Kelvin, also produces many X-ray waves. By analyzing the amount of gas being pulled in by the black hole, astronomers can measure the mass of the stellar mass black hole. Other methods of locating stellar mass black holes include using gravitational waves. Light is not the only way to estimate and locate a particular black hole. Gravitational waves were originally predicted by Albert Einstein's theory of general relativity in the 20th century, and in a nutshell, it explains that the very fabric of space and time are curved by matter and energy. The curved space fabric then controls stellar, planetary, and galaxial movement. The detection of gravitational waves helps gain new information about normally hard-to-find astronomical objects, such as stellar mass black holes. Although first predicted by Albert Einstein, the actual gravitational wave detection only developed in 2015. However, this new technology is being used to conduct further astronomical research on not just black holes but other astronomical objects as well. For example, in May 2023, a gravitational wave detector found a black hole 650 million light-years away. The detector also found the mass of the objects detected. Remembering that the TOV limit is 1.5 to 3.0 solar masses, many astronomers hypothesize that this range leads to the fact that there must be some sort of mass gap between the densest neutron stars and the lightest stellar mass black holes. The black hole detected by the gravitational wave system, named GW230529, is a black hole that falls within the mass gap, as it only has a mass 0.75 times the mass of the Sun, well under the TOV limit. Even though this black hole candidate may not even exist and could just be a product of random gravitational wave noise, it highlights the potential research opportunities and the future of stellar mass black holes. There are roughly 26 known stellar mass black holes, and the ones I found most interesting are A0620-00, which is a stellar mass black hole with a mass of 3 to 13 solar masses, a diameter of 10 to 25 miles, and it is 2,800 to 3,400 light-years away in the constellation Monoceros. This stellar mass black hole is particularly fascinating since it is the closest known stellar mass black hole to Earth. Additionally, I found it odd that there was such a large margin of error for the solar mass value for this black hole. The other one I found interesting was XTE J1118 plus 480. So this stellar mass black hole has a mass of 7 solar masses with a diameter of 26 miles. It's about 6,000 light-years away and is in the constellation of Ursa Major. So this one stood out to me because it had a very precise solar mass and radius value and didn't seem to have the same margins of error as the other SMBHs. These are my references, and thank you for your time today.